Powered by youth, driven by purpose. Welcome to the Brain Camaraderies podcast, where we spark conversations, spread neuro-awareness, and stand for change.
Hello everyone, and welcome back to our podcast. I'm Yadika Sivanagothakrishnan, the CEO and founder of the Brain Camaraderie, which is a youth-led nonprofit dedicated to supporting patients impacted by rare neurological diseases.
I'm Satvik, and I'm one of your graphic designers, and today I'm going to be your co-host. Please welcome Dr. Alberto Espay, a professor of neurology and endowed chair of the James J. and Joanne A. Gardner Center for Parkinson's Disease at the University of Cincinnati. Dr. Espay is a prolific researcher with over 350 peer-reviewed articles and 10 books, which includes the Prose Award-winning Brain Fables. He's also a leading advocate for precision medicine and neurodegenerative diseases. His work challenges unconditionally accepted beliefs in Alzheimer's and Parkinson's. It also pushes for a rethinking of diagnostics, clinical trials, and therapeutic strategies through biomarker-based approaches, notably his 2022 TEDx talk, Parkinson's and Alzheimer's, The Solution in Sight.
Thank you, Satvik, for that introduction. Dr. Espay, could you begin by sharing a little bit about your background into this complicated field and maybe any experiences that compelled you to work with conditions like Parkinson's, Alzheimer's, and conditions like that?
Absolutely. Well, thank you, Jathika and Satvik, for the invitation and for hosting me. I got interested in the area of neurodegeneration through my training in neurology of aging, and particularly with an interest in movement disorders. I'm a movement disorders neurologist, and because the most common condition among movement disorders is Parkinson's, and because Parkinson's is a good example of a neurodegenerative condition, I became quite interested in understanding what is it that we call Parkinson's, and why is it that we call Alzheimer's, and why is it that there are all these differences between them, and what might connect the thread between normal aging and accelerated aging, which is what Parkinson's, Alzheimer's, and other neurodegenerative diseases are. I see patients that have these conditions, and I have been doing research on a variety of topics, but including trials. And as we began to start trying to disease modify these conditions, disease modification is a term to imply that we're trying to slow the progression, and we got nothing for our efforts, I began to think that we needed to look into the foundations of why we defined Parkinson's in the way we have, as well as Alzheimer's and other conditions, and might that need to be rethought so that we could conceive of alternative ways to get into disease modification in a manner that would finally give us some meaningful answers. So that's really at broad strokes how I came to do what I do. I spend half of my time seeing actual patients and then the other half doing research.
Okay, that's very nice to hear, Dr. Espay. And so I have a question for you. You're known for challenging the principles of neurodegenerative disease research. So what foundational beliefs or narratives in the field do you find the most problematic? And why do you think that it's crucial to question them right now?
Well, Satvik, the definition of all of these conditions as the product of accumulation of proteins is the most difficult for me to digest. In reality, the conditions we're dealing with are all of loss. There is degeneration with loss of neurons, with losses of proteins, with loss of a variety of neurotransmitters. We lose quite a bit, and somehow we've framed the conditions as being one of gain. Now, when you frame the cause of a problem as a result of the gain of something. Most often you're dealing with cancers. Cancers are the result of an abnormal gain of something, in many cases, proliferation of cells. Neurodegeneration is the opposite in many ways. It's the loss of something. So there are many biological pathways that end up giving rise to cancers, and those are going to create the rapid acceleration of cell formation. But then there are many biological changes that lead to the rapid degeneration of cells. That is what degeneration is about. We have borrowed from the field of cancers the one thing we shouldn't have, which is the idea that these diseases are caused by an increase or an accumulation of proteins. It is absolutely false. If you measure the proteins in any way, the matter, those proteins are actually depleted. We measure those in the spinal fluid, which is the closest thing that allows us to understand how the brain is functioning. And invariably in Parkinson's, the key proteins are diminished. Synuclein is the key protein in Parkinson's, but A beta 42 is another, is depleted, as it is in Alzheimer's disease, for instance. And so what we've defined these diseases is because there is a transformation of these proteins as they become non-functional that turns them into clumps, and those clumps we have wrongly thought of as the causes of the problem. So I think that is the framework of these diseases of accelerated aging, because something is increasing, and if we target that which is increasing by removing it, then that should be the solution of our problems. And of course, that has not turned out to be the case. And I've argued that the reason it hasn't turned out to be the case is because that idea, while has a logic of its own, is actually not true.
Thank you for those detailed explanation. And I like how you differentiated those two, aspects. That's a really interesting way to think about this. Now let's move on to Alzheimer's. And I wanted to ask this question after coming across some of your work. Could you explain why you believe calling Alzheimer's an autoimmune disorder is fundamentally flawed? And could you explain more on that?
Yeah, so Alzheimer's is undergoing a variety of different transformations as it is being thought of, to try to make sense of it, because we've just failed with so many different strategies that we kind of come up with new ideas as to what Alzheimer's is. The idea that in this situation Alzheimer's can be an autoimmune condition has come because when certain inflammatory markers or certain antibodies are measured, they may be high. That is not an indication that we're dealing with an autoimmune condition or even an inflammatory condition of any kind. Going back to general principles, if you have loss of brain, if you have loss in general, whatever is going in the opposite direction, whatever is gain, either in absolute or relative terms, is most likely to be reactive or even protective. So that if we were to target the inflammatory markers that are increased in Alzheimer's, we would probably just see the same that we've seen in other strategies, which is that there won't be any benefit. So we often are approaching Alzheimer's and other neurodegenerative diseases by trying to understand what goes up, and what goes up we think must be the cause of the problem. I'd argue it's the opposite. What goes down is what we're losing and what we need to replenish. What goes up is likely part of a compensatory reaction, maybe part of what we refer to as homeostasis, the idea that the body is trying to preserve its own equilibrium, and in the context of losses, it increases the relative or absolute values of something, and that something is important. By the way, the other reason why Alzheimer's couldn't be an autoimmune condition is because the key aspect to an autoimmune condition is that there is an autoantibody, an antibody against the self, that then if you isolate it and you then give it to a model, an animal model, you elicit the disease. And then, of course, the key demonstration would be that then if you eliminate that antibody from that model, the disease would be gone, and that has never been demonstrated. Essentially, is an interesting idea. I think it's part of an effort to try to move away from the most dominant of all ideas in Alzheimer's, which is the amyloid cascade hypothesis. But just because it's another idea doesn't mean it's a better idea.
All right, thank you so much for the explanation on why you think Alzheimer's isn't an autoimmune disease. And so, considering other neurodegenerative diseases, in your work, The Brain Fables, you co-authored a blueprint to conquer neurodegenerative diseases. Could you tell us more about this specific blueprint?
Yes, absolutely. What we looked into through the book is the milestones of our history, or the history we've told ourselves as to what Parkinson's and Alzheimer's are, as examples of, again, neurodegeneration or accelerated brain aging. And in that process, it becomes clear that the clumps of proteins that have defined the diseases are not the causes, but the consequences, the markers of a reactive brain, but not the makers of either disease. But what we made the case of in the book is that the more of the pathology there is, the less of the normal proteins from which that pathology forms remains in the brain. And I can demonstrate. I have a little something to demonstrate what I mean, because sometimes it's very helpful to demonstrate it. I don't know how many people will be listening to this in audio only, but I wanted to present a strand of wool. This is what a protein might look like in its normal state. It has a string of amino acids that connect to each other as if this was a single strand. And what happens is that this must be in a very soluble state. Soluble means it can be dissolved in water, and because it can be dissolved in water, it can be quantified by measuring the water we all have around our brain, called the spinal fluid. And so when we do a spinal tap, we can get some of that fluid and measure how much of the specific proteins we have. So these proteins are all over the brain, and of course they can be measured in the spinal fluid. And what happens in diseases of aging is that there is something the brains are always fighting, and it varies in different people. I'm going to use a little ball here to demonstrate something that could be a virus, could be a nanoparticle from a toxic exposure. It can be a biological change of sorts. And what then these proteins do, that they undergo a phase transition from the liquid or soluble state that I've mentioned to an insoluble or solid state. And that means that they are going to acquire a so-called cross-beta configuration, because they're going to be pretty much undergoing this transition as they are reacting against that bit of something that shouldn't be in the brain. And as they do that, and the exposure continues, then there is essentially the formation of these clumps. Those clumps are called pathology. We recognize them when somebody has an autopsy, somebody who's died of a disease of aging. In the autopsy, there will be lots of these clumps, and we use them to call the disease a name. If this is mostly amyloid plaques, we say that is Alzheimer's. If this is mostly Lewy bodies, we call that Parkinson's. If this is mostly something called tufted astrocytes, we call that progressive supranuclear palsy, etc. We have names for the diseases we think the clumps created. But in the book, what we've done is present an alternative idea about why this happens. Well, if you have this, what happens is that the proteins that became the pathology or the clumps become less and less, the brain is trying to replace them, but in the context of an ongoing phase transition, if the brain doesn't keep up with its supply, the demand of these proteins for this reactivity, which is normal, which is just the normal reaction of a normal brain under an exposure that shouldn't be there, then the supplies become less and you have less of the proteins. So that the book is a way to remind us that there are always two sides to any story, and that the pathology or the clumps that define the diseases are one end of that story, and the other end of the story is, of course, the normal proteins. And that at a population level, these things are inversely correlated. The more that you have pathology, the less of the normal proteins you may have. However, what we've shown through a variety of different avenues in our publications is that the difference between people who have pathology and disease versus people who have pathology and are normal is how much of the normal proteins they still have. If they are able to generate quite a bit of the normal proteins, in fact, they are normal. That's something that has been demonstrated very elegantly, both in patients with what we call sporadic Alzheimer's, meaning people who have the Alzheimer's pathology. The more of the normal protein they have is about a particular threshold, the more normal they are. And in fact, the more they have at baseline, we've recognized that even in people who have genetic mutations, have a longer time to developing the disease we think that pathology produces, which is not true. So I guess the template for us to think what we could do is that in the context of somebody who has a disease, rather than eliminating the pathology, what we're proposing is we need to increase the levels of the normal proteins. And we already have established thresholds of compensation above which you would expect rescue. So rescue medicine is what the book is meaning to try to bring forth, that we know that these proteins are low. The lower the levels of the proteins, the more severe the disease is, the more rapidly it progresses. Then it behooves us to use protein replacement strategies to try to help with the disease. So that is rescue medicine, and that is a concept that was put forth by Brain Fables.
Awesome. Thank you so much for explaining the brain fables more in detail. And you were talking about how, how many clumps determine, what disease or how much of the disease there are. But in your previous work, you also talked about how pathology does not always mean pathogenesis, so like the disorder. So could you explain more about this? Like this could be where you think this could actually be a result of aging instead of, disease. So could you explain more on that, and how this may affect our understanding and approach of diseases like Alzheimer's?
Well, Jatika, the best way to respond to that is to say that as we age, all of us are accruing pathology in a linear fashion. A simple majority after the age of 75, 80 years is going to have pathology, amyloid plaques, Lewy bodies, tufted astrocytes, a variety of different pathologies. But very few of those of us with pathology will go on to develop disease. So there is a difference between how much pathology you have and how often you would be developing a disease. In the Mayo Clinic study of aging, it was shown a few years back that by the age of 85, 60% of amyloid positive, so plaque positive individuals, people with pathology that is we today define as biological definition of Alzheimer's, about 60% would have it. Only under 10% have dementia. So there is a fivefold lower prevalence of dementia than predicted if the pathology were pathogenic. And that's why I mean that pathology means pathology. It's a marker, not a maker. But we have made it out to be pathogenesis or exchangeable with pathogenesis. In many lectures in the past, people would talk about pathology and pathogenesis in the same sentences, as if these two were equivalent. I worry that in the brave new world, there's beyond calling pathology and pathogenesis exchangeable, but now we're in a world in which we are often using pathology as equivalent to biology and as equal to disease. And so sometimes we say, well, the disease propagates from one part of the region to the brain to another. And this is sort of a description of the pathology propagating from one region. But we speak of the disease propagating because we equate pathology to disease. So I think part of the problem has been on having tests that we today can recognize as being really helpful tests to identify pathology. And because we don't have to wait for the autopsy to demonstrate that there is a presence of pathology, now the identification of pathology in a living individual is a way for us to say we have identified the biology, and that's not true. There are many biological routes to Parkinson's, many biological routes to Alzheimer's. All of them converge on just a few pathologies. The pathologies are very different to the biologies. And so we have good tests of pathology now. Some of them are imaging, some of them are spinal fluid tests, some of them are blood-based biomarkers. But by calling them biology, we are violating what they are. They are identification of pathology. So pathology is not equal to pathogenesis, is not equal to biology, is not equal to risk, is not equal to disease. And the more we use pathology as synonymous with any of these other terms, the more confusing the story gets, and the less likely it is that any research effort inspired on the idea that these terms are equivalent will ever pan out to help patients.
All right, thank you so much for the explanation on what you meant by pathology doesn't mean pathogenesis. And going back to that, you direct the Cincinnati cohort biomarker program, which is made to match specific patients with therapies based on biological suitability, which is regardless of the clinical diagnosis. And so, what specific errors in traditional diagnosis does this precision medicine aim to fix? And in what ways do you think it would impact the patient going forward?
Well, thank you, Sadvik, for that question. This is then the change from what I mentioned earlier by rescue medicine into precision medicine. So rescue medicine, as I mentioned, we can lump because all we need is one test, and that test is how low the proteins are to know that if we can increase them, we can rescue their levels and rescue the clinical aspects associated, we think, with that loss of proteins. Precision medicine requires splitting, not lumping, and to split people into their biological subtypes. We created this study, the Cincinnati Cohort Biomarker Program, whereby everyone obviously is recruited with a particular diagnosis, Alzheimer's or an Alzheimer's-like condition, Parkinson's or a Parkinson's-like condition. The label we use is not meaningful. We're not saying, what's the difference between people with Parkinson's disease and tremor versus people with Parkinson's disease and no tremor, or between Parkinson's and Alzheimer's, or between Parkinson's and control? Those are not the questions we're asking. We don't want to find more biomarkers of Parkinson's because we don't know what they apply to. Whatever is common across a population, if we recognize that Parkinson's isn't one disease, if we recognize that Alzheimer's isn't one disease but many, then whatever is common across them all cannot be relevant to the individual. So what we've done with this study is turn the tables around, and we are now using the independent variable of the biological signals of interest, and I'll tell you in a moment what those are, and the dependent variables are the diagnosis we use. And it's exactly the opposite to what I've just mentioned. Rather than saying, what's the difference between people with Parkinson's versus people without in terms of the biomarkers, we're saying, given this biomarker that is actually relevant because it connects to a biological subset of individuals with an abnormality that happens to be important to recognize because there is a treatment that corrects it, who are they? And now we go into the diagnosis. So we are inverting the order of development. And so the biomarkers we're looking for are individualized assays that tells us something about someone's unique biology. When we make a diagnosis at the bedside of someone, let's say we're saying, let's say Alzheimer's disease, when we say to an individual, based on the information I have on your examination and an imaging test or a spinal fluid test, you have Alzheimer's, we should say thereafter, we don't know what that means. That is what an oncologist would say to somebody with liver cancer or breast cancer or whatever cancer, right? Here you have a test that says you have cancer. We don't know what that is. We need to do a variety of different tests to be able to identify what disease you actually have, to then know how to treat you. We don't do that. We say, well, I did one test, and that test confirms that, in fact, you have pathology. The pathology is consistent with the clinical symptoms you have. The pathology is amyloid, and the clinical symptoms is forgetfulness. Well, that means you have Alzheimer's disease. End of story. We don't go through any further layering. We're not sophisticated as our oncology colleagues are. So what the biomarker program is intended to do is for now a research program, but I hope that it'll eventually become standard of care, is to be able to tell our patients, we're giving you a diagnosis, but it's a placeholder diagnosis. We don't really know what that means to you. We know that you're blazing your own trail because everybody's different, but we now need to figure out why it is that you are so unique and how you are not common to everybody else, how you're different from others, even though you might share the same diagnosis. That's what this study is all about. And it requires splitting people into the unique subtype into which they belong, because that is going to give us the opportunity to apply the principles of precision medicine. So that is, of course, not to mean that it is exclusive mutually exclusive from the rescue strategies. But you can imagine rescue strategy plus precision medicine would be a powerful combination. Some people might do just fine with rescue, but in many cases we need to get to the bottom of the biological root of someone's condition, and that will be the first success of precision medicine, of really getting to someone's actual disease and treating it. The first success will be very small under the principle of precision medicine, because that's what happens. You get very small subset of individuals with a much more specific, biologically homogeneous finding. And then once you get success, you begin to try to add more people to the pot, so to speak, by maybe adding another therapy, etc. You can expand the radius or the coverage of people, and that's what we would eventually like to do. We hope that this is the decade in which we're going to realize the first success of precision medicine, because we would have identified at least a handful of people about whom there is actually a therapy already out there that we can use if we knew who those therapies are for.
Yeah, it seems like you guys are already doing so much with this precision medicine. And beyond just what's happening in this study, or just like beyond, how do you see precision medicine evolving to address more on the heterogeneity of neurodegenerative diseases?
Well, I think is a recognition that because what we see in our patients is so heterogeneous, even if we give them one particular diagnosis, the way that each patient presents to us is very varied. In fact, we ask people not to compare themselves to others, and not to think that just because we're giving a diagnosis, we're presenting them with a script of what is to follow. In many cases, there isn't really a way to predict how anybody will do. A lot has to do with how their unique biology is. A lot has to do with how they think about the world, or what kind of motivation they have, how active they continue to be, how socially engaged they are, etc. There are a variety of different things that determine how someone will do. We neurologists have very little power, really. Even with all the medications we could potentially use to help with the symptoms, we have very little power to helping with their condition long term, unless people get really busy with making sure they don't let this disease get the best of them. Just to exercise, eat healthy, but in recognition of that heterogeneity is why we need to act as if we mean it when we say so. I think what has happened in the past, Jessica, is that we have said to our patients, "You're very unique. We've recognized that for a long time. You know, don't ever think that somebody you just sent in a wheelchair with your condition is where you're heading. So not everybody goes that route. We don't use the staging precisely for this. So be mindful. You're blazing your own trail for sure." And in the next sentence, we say, "But be hopeful. We're going to have a treatment that will cure Parkinson's or will slow its progression." And those two things cannot follow. One of them is not true. The two can be true. You cannot say that Parkinson's is very different, so everybody is having their own disease, and then follow that up by saying, and one day we'll have a biomarker of Parkinson's that's relevant to everyone and a treatment that will slow Parkinson's progression. That's not possible. And so what we've been doing is literally trying to act as if we mean it when we say no two people are alike. And so that's trying to kind of address this issue of the heterogeneity.
Got it. Thank you. And so considering like the heterogeneity of the people and how they think about the world, like you said, and other factors like that, could you give us like a specific example of when you've seen a certain bias, especially in collecting data from the context of your work?
Well, that's it's a tough issue to fully get your head around, but let me just perhaps paint the situation in terms of trials that have been done for therapies that presumably slow progression. They are called neuroprotective therapies. What we do with those therapies is we try to do exactly what you just said, Sadvik, which is we're going to try to get people who are relatively the same. So we create a set of stringent inclusion-exclusion criteria. They must have a certain age, they must have a certain number of years from the symptom onset, they must not have cognitive difficulties, they must not have psychiatric complications, right? You start creating a set of rules as to what kind of condition you have because you want that to be homogeneous. That's in the eye of the beholder. To us, we think of them as less heterogeneous simply because we're creating all sorts of criteria and rules to rule out a lot of people from the large pool of people on the concept that now we have a more homogeneous subgroup of individuals. But they are homogeneous based on the clinical features we give them or we created for people to fit in, not homogeneous biologically. And since all of our therapies are having a biological action, we think, the therapies that are making it into clinical trials, then, as you can imagine, this is giving us only the illusion that we are being homogenizing the population and therefore increasing the odds that the particular therapy we're testing is going to succeed. It's not going to succeed because it doesn't matter how homogeneous it may seem clinically, there is vast heterogeneity molecularly or biologically. And so, and that's, in my mind, it is the most important reason why we have only failed in the nearly 5 decades that we've been trying to slow the progression of Parkinson's and Alzheimer's. We've completely failed because we've treated these diseases as if they are diseases, and they are not. They're syndromes. And syndromes, collection of different diseases. We have name them diseases, but in reality they are not. It is in part the problem of a century-old adherence to a model of neurodegenerative diseases called the clinical pathologic model, meaning that if you have a set of clinical features and a particular pathology, that is a particular disease. We defined that a century ago. That model was helpful until it wasn't. At some point, it became outdated. It is outdated now, but we are still insisting that is a way to define the disease. That's why the biggest, quote, breakthroughs are tests of pathology, because the clinical pathologic framework is the one that we use for defining diseases and approaching them from a research perspective. Well, if that's the model, then gosh, if pathology is one big piece of the clinical pathological model, therefore, if you have a test for the pathology, we are going to be much closer to the cure. That's how we've been creating this illusion that we're so much better by doing what we're doing, creating tests of pathology, and then not only creating tests of pathology, but interpreting them or misinterpreting them as tests of biology or pathogenesis or risk or disease. Very unfortunate. We've come down a difficult route. Unfortunately, by the way, it doesn't matter how beautiful our ideas have become. If they are false, nature doesn't give a damn. You can never build anything meaningful out of a house of cards. If you have built an infrastructure that you think is beautiful, magnificent, logical, but false, it won't work. And so my sense is, back to your question, the heterogeneity is going to be there no matter how clinically clean a particular subset of individuals we think are. In fact, once we start finding biologically homogeneous subsets, my sense is that they will still be clinically heterogeneous. That if we find a particular biotype of, say, Parkinson's, that they are going to be different people. But we won't be able to say, based on the combination of a postural tremor, executive dysfunction, and hallucinations, that will predict the particular connection with this particular biological subset. I don't think that will ever be that way. I'm a clinician, and I love semiology, which is a study of the symptoms and signs. I like to characterize patients as well as I can from the way they look and from my neurologic examination. But from there to say, if I do so, I will be one day able to predict their underlying biology, that's a leap of faith that I don't think we will ever be able to get there. And it's wishful thinking. I of course, there was a time I thought we will one day get there. Now, I no longer think so, and I think that we are very much overdue for a paradigm shift, not unlike the way Thomas Kuhn suggested in his seminal Structure of Scientific Revolutions book, which I think is an important read for all of us.
Great. Thank you so much for the explanation on how the bias works in collecting data. And I really liked when you said, even though you build something, and if it's false, there's like no point in doing it, and nature doesn't care. But switching things up a little, could you talk about your clinical experiences of being a principal investigator on high profile trials like RISE PD, which tested IPX203, the medicine, against a regular levodopa pill, and like that study, Advanced Parkinson's Disease? And what information do they have on your critiques of disease modifying trails for neurodegeneration?
Well, thanks for asking that question, Sadvik. Actually, that trial, the RISE PD for what was called IPX203, and now we call it Crexont because it was approved by the FDA, is actually a good example of a symptomatic therapy that delivers levodopa, which is a neurotransmitter that's deficient. Here, a good model of a deficiency that is being rescued with exogenous levodopa with the technology that delivers it in a continuous manner, well, in an extended release manner. That's what that's about. And it gives me the opportunity to tell you that disease modification is the idea behind what we've been talking until now. You're bringing now the topic of symptomatic enhancement. So levodopa is the most important treatment for Parkinson's, and there are a number of trials, such as RISE PD, which have been designed to improve the the dopaminergic tone of the brain through making old therapies better or to creating new therapies that improve the tone of dopamine or norepinephrine or serotonin, etc. And so those are symptomatic treatments, very different than disease modification. In symptomatic treatments, we can also lump because most people with in fact, everyone with Parkinson's should have dopamine deficiency. The symptoms we recognize at the bedside as distinctive of Parkinson's are symptoms that come as a result of deficiency of dopamine. So if we increase dopamine via levodopa, this medication is the one you mentioned, that would allow us to help people's symptoms. It won't change the trajectory of the disease necessarily. In fact, it shouldn't. What will change the trajectory of the disease is that once they have levodopa, they can exercise, they can move about, they can have a more engaged social and occupational lifestyle. Therefore, they're going to live longer. In that sense, that's disease modifying, but not directly through that mechanism. So we do a lot of trials in fact, I'm more interested in trials of symptomatic therapies than I am in trials of disease modification, because disease modification trials still today are done in a manner that targets people by virtue of their clinical pathologic characterization. So people who have Parkinson's with a test that tells that they have Lewy bodies, right? That's not good enough for me. I want to know can we use a test that defines how different they are and how vulnerable they are to the particular molecule that I'm trying to determine its efficacy in the clinical trial for disease modification. But for symptomatic therapy, I don't have to be that sophisticated. I know that they have Parkinson's. The symptoms tell me that they have a dopamine deficiency, and if I'm now being asked to participate or to work on a trial of a dopamine enhancing treatment, I'm very happy working on it because I know people will more likely get better. And so just to summarize, we have symptomatic therapy development, helping the symptoms but not changing the trajectory of the disease. Levodopa would be a good example, and many other dopaminergic therapies. And then disease modification, which in most cases, except for rescue, requires splitting. No longer you're dealing with just Parkinson's. You want to deal with Parkinson's with a specific biological subset. And that has been the difficult step of development that we're trying to change, because unless we get to that change, we won't have a success in precision medicine, which is the key part of disease modification.
Awesome. Thank you for explaining that in detail. And throughout this entire interview, we were talking about, all these alternative frameworks that not a lot of scientists would have considered. And even in some of your work, such as the brain fables, has also been listed. So considering the slow pace of the changing scientific models, what practical steps do you believe are most effective in pushing the neuroscience community as a whole to consider and adopt these alternative frameworks?
Thank you, Jathika. My top one recommendation is to be able to use every single experiment and clinical trials in humans as an opportunity to test a hypothesis. If you do a trial, you're testing a hypothesis, or you should. Every field of medicine does trials because it is the only mechanism we have to test a hypothesis of therapeutic relevance in humans. We don't do that. And that would be the one cultural change that might allow us to get there. When we do trials, we're saying to ourselves, we're doing so to learn, which sounds, of course, magnanimous, and we're doing that to test the safety and efficacy of molecules, which, of course, is important. But we must remember that we're doing the trials because we're testing hypotheses. In neurology, we don't have a good reputation of doing trials to test hypotheses. And in fact, if you look at the reports of most of our trials, there is barely a mention of the hypothesis. It should be obvious that if I'm using a treatment that increases mitochondrial function, that increasing mitochondrial function should improve people, that is a hypothesis that need not be even mentioned. But the reason it's important to mention in it is because when the study is negative, which will be if it's not splitting people, right? If you have a molecule that increases mitochondrial function and you're not selecting people in whom mitochondrial dysfunction is to them pathogenic, then the trial will not work. But if you're not testing it, if you're not formally testing the hypothesis, the excuses you're going to present in the discussion of your paper will be that the dosage might not have been good enough, that the penetration in the brain wasn't good enough, that the target engagement wasn't good enough, that the sensitivity of the endpoints, the accuracy of our measurements wasn't good. And the favorite excuse that we give ourselves is that the patient population was too advanced. The people were too far out with their disease. Imagine if our oncology colleagues would have said the same thing. Oh, well, this treatment for cancer failed because people had the cancer. We need to treat them before they have cancer. And while it is always better to treat people earlier, if you treat people earlier, still with not knowing what you're trying to change and in whom, that's still going to be a failure. The successes in early treatment in the field of oncology have come when they have treated people with cancer in an advanced state, have made a difference. They determine what the biological connection is between the treatment and the patients, and then they use that biological test, a biotest, a bioassay, and deploy it earlier and say, well, if we can then capture people at an earlier time point, then of course we want to start the therapy there. But we somehow think that if we were just to do all the trials in an earlier state, everything that has failed would have now worked, and that is not true. So the first idea here would be to be able to have an opportunity to use every single trial as a test of the hypothesis. Until we do that, we'll continue to be testing molecule after molecule after molecule, but the same inspiring idea behind each of the trials.
Thank you so much for all your responses. What is one powerful message about the future of disease research that you could share with our audience of potential aspiring neurologists, researchers, anything science?
Well, thank you, Jessica. That's a very important question, and I must admit a very difficult answer because I don't think there is a single way to ensure that we will get to a point where if applying a particular set of techniques, somehow success will happen. But what I would say is that we must strive to treat every knowledge that we acquire carefully. Nothing should be settled. No, not in science at least. And the reason is that if we find that anything is settled, then we stop thinking. And that applies to everything. It's not just research. It's about even a patient's diagnosis. If we say, well, I've said this was Parkinson's, and then some other data happens to come across about that particular patient, you must change your diagnosis. So at least you need to rethink that something else might be going on. Same thing with scientific ideas. And so research is predicated on the notion that you're constantly learning new things, including new things about things you thought were settled. Our patients deserve from us to be absolutely detached from any ideas. It's okay to create ideas, but it's not okay to fall in love with them. It's important to ensure that we remain as objective as we can and treat, in the Popperian model of science, every idea as false until proven otherwise. And it almost never gets proven otherwise. So there is always a more likely explanation, but not a certain explanation. And that's very, very important. I think that's going to be the key ingredient to the success of any research program, to continually questioning that which we think we know.
Okay, thank you, Dr. Espay. Thank you so much for being here today and for all the time that you put forward to explaining to us and for answering our question. And also, we're really grateful for everything you've contributed to research and advocacy for neurodegenerative diseases. And we know that our listeners will learn so much from this podcast. This has been such an inspiring conversation. Thank you so much.
Thank you so much, Savik. Thank you so much, Atika. It's been a wonderful pleasure to be with you all. I wish you the very, very best on this endeavor and many others, and I'm happy if we get together in the future and have another conversation.
Of course, thank you. And this interview will be available soon on Spotify, YouTube, Apple Podcasts, Podbean, and our nonprofit website. And thank you so much.
You're very welcome.
Thank you.